Hello students, welcome back. We're going to continue today with signal transduction part 13. So we're nearing the end of signal transduction, but that's a big part of biochemistry. That's why we're talking about it so much. Let's see what we did last time. We talked about how you make norepinephrine from tyrosine. We talked about that. Not going to go over that again. Also last time, yes, we talked about the different adrenergic receptors. What makes them different? I'm going to actually redraw this because it's not as clear here. So let's redraw our adrenergic receptors here. So we're just going to draw the ends of the adrenergic receptors. Let's get a good color here. Okay. The catechol end. We're going to make all the catechol ends look alike. Well, let's do this, if you all will allow me. I'm just going to make like a box, and I'm going to adjust this box here. So here's my box, and I'm going to fill it in here. Because rather than drawing the same thing 3 times, this is going to make it easier for us. Or for me, kind of. And so this is the end of the receptor. Okay? That's the end of the receptor. What I'm going to do now, I'm going to make a cutout of this for my catechol end. So my catechol end is going to bind here. Okay, I cut that out. That's where my catechol is going to bind. And my amino end is going to bind here. Okay? Now what I'm going to do, I'm just going to make a copy of that because that's going to make it easier. And so let's say that this is the situation where we're just going to do 3 of the receptors. Just going to do 3 receptors. Okay? And this one is going to be, this first one, we won't do alpha 2. We'll do alpha 1, the alpha 1 receptor, and we'll do the beta 1 receptor, and we'll do the beta 2 receptor. Now, how do they differ? I'm going to just put all these on the same level. Okay, how do these differ? Now, the beta 1 has a very small amino binding end. Beta 2, however, that's alpha 1. Beta 2 has a larger, it's going to be larger here. Can you see that that's larger? It's larger for beta 2, for beta 1. And for beta 2, I'm going to make it even more pronounced. This end is even bigger. Does that make sense? Are we ready to go with this? Okay, and so this is going to be the catechol. Okay, this is the catechol end. Catechol, catechol, catechol. They're the same for all of the agonists. And but for the amino end, they differ. And so we have different compounds that bind these receptors. If we looked at something like epinephrine. So if you don't mind, for epinephrine, I'm just going to draw the amino end of epinephrine. So I'm going to let this this is going to be, that'll be the catechol end of epinephrine. And then the amino end of epinephrine is going to be NH, and then there is a CH3. And so epinephrine can bind to the alpha 1 adrenergic receptor pretty well. Binds pretty good there. It binds alpha 1. It binds alpha 2 pretty well. And it binds alpha 3. Alpha 1, beta 1, and beta 2. It can bind all 3 of those receptors. epinephrine can. And so it binds all of these with pretty much equal strength. Epinephrine does. If we looked at something like norepinephrine, so I'm going to put, if y'all don't mind, I'm just going to make a copy of this. Okay, now I'm going to make norepinephrine. How does norepinephrine differ from epinephrine? Instead of having a methyl group, norepinephrine only has a hydrogen there. So I'm going to move epinephrine out of the way for now, and let's look and see how norepinephrine binds. Norepinephrine binds alpha-1 pretty good, pretty strongly. Norepinephrine binds beta-1 pretty well also. But norepinephrine, it binds beta-2, but not that strongly, because because the amino end is not really big enough to fill up the binding site. And so norepinephrine doesn't bind beta-2 as well. It doesn't bind beta-2 as well as alpha-1 and beta-1. Does that make sense? Does the concept make sense? Because epinephrine has a bigger amino end, so it's going to be able to bind all of them pretty well. Okay. Let's look at another compound. And a lot of people, does anyone in here have asthma? No, anyone? Have you ever heard of albuterol? Okay, very good, very good. Let's look at. Okay, I'm gonna make this one, and we're gonna make a compound here. We're gonna make albuterol. Okay, I'm gonna erase this, and albuterol is gonna have. It's going to have CH, CH3, well, not a CH, just a C. So it's going to have CH3, CH3, CH3. And this is albuterol. Albuterol. And people with asthma take albuterol. And what's going to happen, albuterol is going to try to bind. You think it's going to bind to beta-1, alpha-1 very well? No, it doesn't look like it. What about alpha-2? No. What about beta-2? Well, that's the only one that's left, and it's bigger, so it has to be this one. And so albuterol, I wish I had drawn that a little better. I should have made that bond shorter. That's what I'm going to do here. Let's see here. Let's make that bond a little shorter. I'm just going to grab it here and lift it up. Okay. Let's lift this up here and make this bond shorter. Okay. Now we have albuterol. It should bind a little better now. There we are. So albuterol binds to beta-2. And remember, in your bronchioles, beta-2 relaxes your bronchioles and opens them up. It opens them up. That's why if somebody has asthma, they'll give them albuterol. It binds those beta-2s, relaxes those bronchioles, and now that person will be able to breathe more easily. And now since beta-2, it's kind of specific for this albuterol is kind of specific for beta-2. It doesn't activate your heart as much, because beta-1, if it could bind beta-1, it would activate your heart as well. And so that's why you want to use something like albuterol. Sometimes so we have beta-2, and this is albuterol. We need to find something that will bind to beta-1 specifically. And so if you're a doctor, someone comes to you, okay, let's see if y'all can figure this out then. Under what circumstances, under what situation, well first, Where's the beta 1 receptor found? Primarily, beta 1. The heart. Okay? And so is it a stimulatory receptor or an inhibitory receptor? Stimulatory. Very good, very good. Now, let's say a doctor has prescribed to someone a beta 1 agonist. A beta 1 agonist. So if the doctor gives someone a beta 1 agonist, what does that doctor want to do for that person? What is he trying to do? If someone gets a beta 1 agonist, you want to do one thing mainly. What is that one thing you want to do for that person? Say that again. Increase contraction of your biceps of the heart. Does that make sense? You want to increase contraction of the heart. Now, what would be wrong with a person if you wanted to? It stimulates your heart. It speed. If you wanted to, what would be wrong with a person if you wanted to stimulate their heart? What would be wrong with them? It's beating too slowly. Exactly. And what is that called if someone's heart is beating too slowly? Bradycardia. Exactly. And so you would give them something to if you want to give someone something just to activate the heart, you want to give them a beta 1 agonist. You don't want to give them something that's alpha 1 or beta 2. You want to give them something that's primarily beta 1. So a drug that does this looks like this. So I'm going to make this one. And so it differs, unlike, let's see here. Let's erase this. Now, albuterol has 3 methyl groups, but this compound is only going to have, its CH, and it's only going to have 2 methyl groups, CH3, CH3. And so now, this compound will be able to bind here to the beta 1. And this compound is called isoproterenol. Isoproterenol. Okay, and so what we're going to do here, we're going to name all of these. And so everything should make sense now. We're going to name all of these. And so we're not going to put norepinephrine and epinephrine because they can, too bad there's not really a good drug. There's really not a good drug for just alpha 1. I'm sure there is one, but we won't learn it. But now we want to name these drugs here. Okay, what's this first drug that's made in your body already? So let's see. I'm gonna get up. Well, let's do it that way. You're all right. Let's put it here. And so this is epinephrine. So if I put just epi, that should be okay. Very good. What's the name of this drug here that doesn't have the methyl group? That's going to be norepinephrine. So if I put NE, would you all be okay with that? That's norepinephrine. Under what conditions would you give someone epinephrine? Why would you give someone epinephrine? Allergic reaction. Their bronchioles close up really tightly. You want to give them something that can get in very fast. Epinephrine. So you're going to give epinephrine. Let's see here. What's the name of this drug here that's usually administered through IV? Isoproterenol. I'm about to spell this one all the way out. ISOPROTERENOL. I'm glad I spelled it because it doesn't look like that. Okay. Isoproterenol. It binds beta 1 and beta 2, but we're just going to put it on beta 2 for now. Now, let's mention question. Right, yeah, isoproterenol goes to beta 1. Yes, isoproterenol, remember, because it's the heart for bradycardia. So isoproterenol is going to go to beta 1. Oh, I'm sorry, I said that wrong. I must have said something wrong because more than one person is confused. So, what pathological condition would you use to treat? would you use isoproterenol to treat? Slow heart, bradycardia, exactly. Let's call it that. Bradycardia. Okay. And the last drug here, what's the name of it? Albuterol. Oops, let me see here. Let's see if I'm on the right layer. Albuterol. And albuterol is used to treat what condition? Asthma, not tachycardia. Because remember, all of these are sympathomimetic. All of these are going to increase your sympathetic response. So all of these are going to help you to deal with stress. So this is asthma. I always misspell asthma. I think it's asth and then ma. I think that's right. Excellent, excellent. And so there is a structure-function relationship between our sympathomimetic drugs, drugs that mimic the sympathetic nervous system. Does that make sense? The bigger your amino end is, the closer that drug is going to act, the more that drug is going to activate beta 2s. The smaller that amino end is, the more that drug is going to activate alpha 1s. Make sense? I'm only going to give you, I'm going to give you one more drug. It's a big group of drugs, but I'm going to give you one more drug, and we're going to be through with these. Okay? Let us okay. Let's get rid of this. What is the name of this drug here? Oh, I don't think I need an H there. I always miss that. Okay. What is the name of this compound? Epinephrine. That's epinephrine. Yep. This is epinephrine. Our favorite drug on earth, epinephrine. Now, I'm gonna change something on epinephrine, and I'm gonna make a really famous drug that it's always on the news. You all just didn't know what it looked like. Okay, I'm gonna erase this because it's not gonna be epinephrine anymore. And all I'm gonna do, the only thing I'm gonna do is get rid of these OHs. And it's a big class of drugs that have this can change a lot here. This changes a lot. All of this can change. But the main point is basically a catecholamine, but without those OHs. And this drug can cross the blood-brain barrier. And a lot of people they'll try to make this drug in their labs at home. Amphetamines. These are your amphetamines. Your amphetamines have this. So, are amphetamines going to make you, epinephrine in your central nervous system, is it going to make you happy or sad? Happy. Amphetamines, are they going to make you happy or sad? Very happy. That's why people take them. And they can go immediately to your central nervous system because they aren't very polar. They're less polar, so they can go there very quickly. And so people will risk life and limb to make this. Okay? Okay. That's good. I think everybody understands that. Excellent question. Her question was, which one does this bind to? Which? Nope. 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 Let me show you you something. I have to show you this. I wouldn't have shown you this, but you all have dragged it out of me. Okay. Let's say here, we're going to have our, let's see here, I'm going to make it blank. This is going to be our nerve ending here. And so here's going to be our vesicle with norepinephrine in it. And now, so when it's time for a response, the norepinephrine is going to move. It's going to move. The vesicle is going to move, release the norepinephrine, and then the norepinephrine is going to bind to whatever the receptor is. Make sense? Now, because these amphetamines, because they almost look like the catecholamine, but just don't have the OHs, they can actually cross here. They can actually cross the cell membrane, and then I'm going to just put here amphetamines. The amphetamines are going to start filling this vesicle up, and then when this vesicle gets too full, the vesicle says, I need to get rid of all of this norepinephrine, although it's not a lot of norepinephrine. And then it just goes and it releases all of its norepinephrine, and it's actually the norepinephrine that binds. But it's because the amphetamines coax this vesicle into fusing with the membrane, and it releases. Exactly. You just exactly. That's what amphetamines do, basically. Does it make sense? Does the rationale make sense? Excellent. Now, why can't I'm going to go back a slide and ask you now. Let's look at the structure. Okay. There's epinephrine and there's amphetamine. Okay. Now I'm going to go back to the receptors and I'm going to ask you a question. Why can't amphetamines bind to the adrenergic receptors themselves? Wait a minute. Think about it for a second. Again, the question is, let's look at the structure of epinephrine. There's a structure of amphetamine. What's different about them? Okay. Now the question is, why do amphetamines not bind to adrenergic receptors directly? Why do amphetamines not bind to adrenergic receptors directly? I need you to think about that for 3 seconds. 1, 2, 3. Okay. What did you have? Exactly. If you don't have the OHs, you can't bind to the catechol end because that's what it binds to, the catechol. And that's why amphetamines or non-catecholamines don't bind to the adrenergic receptors directly. Because, okay, let's look here. See, the catechol end, there's a catechol end on the receptor and there's an amino end. But if you look back now at amphetamines, they don't have the OHs. So they're not catechols. So they can't bind to the catechol end. And so because of that, they can't bind to the receptor. You need both of those to bind to the receptor. Does that rationale make sense? It's the rationale that's important. Yes, it's polarity. The one thing about non-catecholamines, what you can do with non-catecholamines, the blood-brain barrier, it resists compounds that are very polar. So something like norepinephrine won't be able to go into the brain very easily because it has those big OHs. But an amphetamine, that's going to activate your central nervous system a lot because bless you, not only does it cause a release of those neurotransmitters, but because it's nonpolar, it can cross the blood-brain barrier really easily. So if you want something to activate your sympathetic nervous system, do you think epinephrine would work better or something like methamphetamine? Methamphetamine. It's going to be a much more powerful stimulant of your central nervous system because of its non-polarity. Does the rationale make sense? Where's Shaw? Okay. Everyone okay with that? Excellent, excellent. Let's see here. I'm going to introduce one other. Now this one, let's introduce one more. I think this will be the last. Maybe this will be the last sympathetic. Oh yes, this is going to be the last one. Maybe. Okay. Let's make ourselves a smooth muscle, because only I'm doing this because there's a lot of research on this one, of course. Let's say here we have a smooth muscle. Okay. A smooth muscle in the blood vessel. There's a smooth muscle in the blood vessels leading to the penis. Smooth muscle around the blood vessels leading to the penis. Now, in order to get penile erection, do you think we want to close those blood vessels to not let blood in, or do we want to open those blood vessels? You want to open those blood vessels. So do you want a stimulatory receptor or an inhibitory receptor? I'm kind of confused. I'm kind of throwing you off here, because this is not, penile erection is not a sympathetic response, but the signal transduction is important. So let's talk about what actually happens. You release this gas. There's a gas that you release. I want to make sure I get this gas right. Okay. And this gas is going to be nitric oxide, NO. Okay. And this NO is going to go into these cells. And in these cells there is going to be an enzyme. Very happy enzyme. And the NO is going to activate this enzyme. And this enzyme is going to catalyze the conversion of GTP into cyclic GMP. So that's the first step. There's this compound. What do we say the name of this compound is? Nitric oxide. And that nitric oxide. Now, make sure you don't confuse nitric oxide with nitrous oxide. Where would someone use nitrous oxide? Somebody said it? The dentist use nitrous oxide. This is not that. You don't have, what's another name for nitrous oxide? Laughing gas, exactly. There's no laughing gas in the penis. So we have nitric oxide. Okay, let us continue. Nitric oxide goes into the cell. It activates this enzyme that converts GTP into cyclic GMP. We need to give a name to this enzyme before we continue. Oh, let me ask you all this. What is the name of the enzyme which converts ATP into cyclic AMP? I got different answers? Adenylyl cyclase. So, the question is, what's the name of the enzyme that converts GTP into cyclic GMP? Guanylyl cyclase. So there we are. Guanylyl cyclase. Okay. Oh, yes, yes. Let's spell that out. So guanylyl cyclase, Guanylyl. That's a stupid name. Guanylyl cyclase. Bless you. Guanylyl cyclase converts GTP into cyclic GMP. Now, what are we trying to do to this cell? Are we trying to turn this cell on, or are we trying to turn this cell off? Off, because it's a muscle cell around the blood vessels going to the penis, and so we want to relax those blood vessels, and we'll explore that next time. If you would, close your notes. Oh, not a quiz. I'm just going to ask you some questions. See how much you all remember. Okay, this drug is a very general drug. It binds all three adrenergic receptors, alpha 1, beta 1, and beta 2, equally well. What is the name of this drug? Epinephrine. Very good. This drug has a very, very big amino end. It has an isobutyl group on it, and it's used. What's the name of that drug? Albuterol. What is it used for? Asthma. What is the name of the sympathomimetic drug that is used for, that has an isopropyl group on it? Has an isopropyl group. CH, isoproterenol. That's why it's called isoproterenol. Okay, what receptor does it bind to pretty well? Beta 1. What condition is it used for? Bradycardia. Very good. What is bradycardia? Slow heartbeat. Very good. What's the name of the class of compounds that are like adrenergic sympathomimetic agonists but don't have the two OHs? They are not catechols. Amphetamines. Very good. Very good. And what is the name of the enzyme that converts GTP to cyclic GMP? Guanylyl cyclase. And last question, what is the name of the gas that's used for penile erection? Nitric oxide. Have a great day, you all.